Good morning, all. Myself Bhadrachar here, GIT University Kanpur. Going to present a topic: Subspace as adaptive approach for blind channel estimation and equalization under the supervision of Dr. Peterson Professor and guide of GIT University. Dr. Abhinav Pandit, my co-guide of the Bhubaneswar. This is the outline of my topic: introduction, the problem description, estimation of channel subspace, subspace partition, simulation, conclusion, reference. Now coming to the part of introduction, the channel equalization has gained significant attention in recent years, primarily because they circumvent the need of training, thereby optimizing the utilization of available bandwidth. In typical wireless communication system channels, multiple propagation results in interchangeable interference. A significant advantage of SOS-based blind methods is their rapid convergence and satisfactory performance attributes that find application across various blind methods. A specific class of technique known as subspace methods is particularly efficient and has been extensively researched. These methods employ subspace decomposition of the data congruence matrix. With the help of configuration signal model, we present a novel blind subspace channel estimator. We delve into the systematic evaluation of this estimation while dealing with a substantial volume of detected facts. Our approach entails the formulation of channel estimator using subspace, a derivation achieved by adaptive inventive cost function. The cost function encompasses a set of kernel metrics representing signals that share a set target combined through the weight sum of errors. Our investigation into the systematic evaluators of this estimator includes analyzing parameters such as mean square error, bias, and convergence under conditions involving a significant number of independent observations. Furthermore, the applications of subspace tracking technique offers a means to adaptively acquire subspace. Now, the second part, the problem description. In communication system, when the interval of the communication symbol denoted as WM and T is the resulting acknowledges signal adheres to the specific model that is outlined in the reference. In the context of the studies, they represent the comprehensive impulse response of the channels, currently white Gaussian stationary process correspondence to reality to illustrate channel assessment and diversity response. It is reasoned that these subchannels are at our disposal that subchannels can occur through either the oversampling of the solitary sensor of the rate as elaborate in reference. In both scenarios, it is presumed that all subchannels have a finite duration of support with the maximum order indicated as Q. These are the estimation channel response. A subspace approach can be used with the estimated channel parameters as techniques to simplify the process. All EQ plus 1 unknown parameters can be collected into a vector denoted as GD vector. These are the equation. Likewise, significance the J plus P plus 1 at fifth column of H by HA, then H0 will be graded as a vector equations. It is convenient to recurrent the applications with the shift matrix J with all ones in the first sub diagonal with the symbol J inverse to denote JT. Although J is singular, J inverse will equal to JT and an identity matrix can express as J0. In that case, all elements of Hj could be situated down or up by J matrix positions. Here R is the identified as convenience matrix which is decomposed R equal to E yn y to Hn by eigenvalue decomposition EVD where R equal to ES UN delta vector with a single noise subspace represented as US and UN. Correspondingly, it can be determined as UN has inverse equal to 0 for all possible J. Under certain assumptions of all subchannels, US and H have the same rank, its value equal is L plus 2. The rank of UN becomes V minus L minus Q. In consideration where the details of the subspace channel estimations. Now the subspace partition. S1 is the equation. R denotes the conversion matrix as the single vector R. Only the model of L dimensional signal vector within a communication system. Here n denotes the count of specific symbols forming the received signals vector corresponding to the real value channel again. Stands with the ith data symbol. Ci is well defined as a kernel matrix and dimensional L into M, where hi is the normal channel vector and size m into 1, and e denotes the adaptive noise vector of dimensions L into 1. In the message symbols of BI, where I ranges from 1 to n to be independent and identically distributed, the symbols which have been 0 and variance is equal. The ith element of the vector E as is also the equation as mentioned. The matrix identify the data vector, amplitude, and L into n signature waveform matrix W as observed by the receiver equations encapsulate the combined impact of the channel and the kernel matrix of the ith intersymbol symbol. The signal model can be more expressed as the follows using the matrix notifications discussed above. Here we represent x equal WTB. Let's donate R is the convenience matrix corresponding to the equivalent vector signal in the equation. The channel parameters are estimated using blind subspace techniques using the R unique substructure to represent the EVD of R as follows. As a result, you can segregate the eigenvectors in the signal and noise characterized through the matrix US and UN, L into N, and L into L minus N dimensionals. The EVD is given can be written as follows: R is equal to ES and UN. The column of ES can form the single subspace, which is the dimensions of n, while the columns of UN consider the orthogonal component known as the noise subspace. Now the simulation, in the simulation parts, it is of subset set of parameters, generate symbols, channel modeling, subspace method, SVD and null subspace, rank check, construction matrix A, channel estimation, MAC calculation, bias calculation, visualization. Now in analyzing part, they analyze simulation results to draw conclusion about the performance of their channel estimation and the equalization technique. As the figure you can see the MSC of channel estimation, and in figure 3 you can see both MSC and OFDM blind channel estimation and bias of channel estimation shown. And simulation of NR MSC. The NRX functions provides the capability of compute the normalized root mean square error by measuring the absolute difference between predict and observed values. In the simulation setup, there is one transmitter antenna and four receiving antennas. The symbols employs 48 subcarriers and process 200 symbols. The cyclic prefix CP has the length of 12, making the total length of OFDM symbols equal to the sum of symbols and CP denotes as Q. The simulation collects J consecutive received OFDM symbols. The order of the channel is specified as L is equal to 4. This is symbols as channel estimation based on NRMSC. And part of conclusion, subspace method estimation and equalization of blind channels has been demonstrated in this paper through extensive analysis. We examined the asymptotic behavior of our suggested estimator under the of a high number of independent Going to the number of kernel metrics and employing carefully selected weights inside the cost of function, we have emphasized the possibility for performance optimization. Is the difference which I have taken for this paper. Thank you.